In this session, we are going to discuss some basic concepts from set theory. What is a set and other basic concepts. Set theory was actually introduced by a German mathematician, George Cantor. In his name, actually, there is a set, Cantor set. There is a function, Cantor function. Then many theorems, Cantor's theorems and all. Here we'll see what is a set first. What is a set? We are familiar with many collections in our daily life, collection of objects, like collection of numbers, collection of flowers, collection of tables, collection of books, collection of countries, like that. So all these collections are sets actually. But remember, every collection is not a set. Only those collections of which the objects are clearly defined, it can only be a set. So we can define a set like this. A set is a collection of well-defined distinct objects. Well-defined distinct objects. Let us take some examples. Consider the set of all alphabets in a word, something like mathematics. You can consider the collection of all alphabets in the word mathematics. If you pick up the alphabets, you can see that M is a letter, A is another letter, T is another letter, H, E. Then the second M is taken, so we take only once when we write a set. Then the next letter you can add is I, then C, then S. So by writing these letters separated by comma and put them in a flower bracket, braces, between two braces. This is the way we write a set. This way of writing a set is called tabular form. So in tabular form, we will list all the objects. And also we will name this set. Set is some name we will give for this set by using some capital letters, say P. P is equal to set MATHEICS. So these letters are clearly well defined because these are the alphabets in the word mathematics. So it is a well defined collection, therefore it is a set. Now let us take another example. The set of all prime numbers less than 20. 2 is the least prime number, then 3, then 5, then 7, then 11, then 13, then 17, then 19. So these are the prime numbers less than 20. So I will call it P1, the set of all prime numbers. 2, 3, 5, 7, 11, 13, 17, 19. The set of all prime numbers less than 20. So this is a set. So there are various type of sets like this you can see in our daily life. And another form of writing a set is set builder form. Set builder form. Now why we go for set builder form? Especially suppose there are infinitely many elements in a collection. We may not be able to write all the elements in the set. These objects are called elements. So in that case, we identify certain a peculiar unique property which is applicable to every object in that collection or every element in that set. Then using that identity, we will write the set builder form. For example, take this example P1. It is actually the set of all prime numbers less than 20. So every number or every element in this set is a prime number And not only that, it is less than 20. So how do we write this in set builder form? This same set you can write in set builder form like set of all x such that x is a prime number less than 20. So here we are using a unique property of the objects which are applicable only to the objects in this collection. That is how we write set builder form. Similarly, this set P, which consists of all the alphabets in the word mathematics set, also you can write in the same way, tabular form. Here, this x is actually a representer of the object. And this x is a prime number less than 20. So, any prime number less than 20 will come in the collection P1, in the set P1. So, you take another example, some set of rational numbers in between 0 and 1. All the rational numbers in 0, 1. Open interval 0, 1. So how do we write that? We cannot list all the elements, or we cannot use the tabular form for writing all the rational numbers in 0, 1. So we go for set builder form for writing the set of all rationals in between 0 and 1. It is written like the set of all x such that x is a rational number between 0 and 1. 0 and 1. This is the way we write set builder form. So both tabular form and set builder form are commonly used, but in certain cases only set builder form or tabular form can be used. In all the cases we cannot use these forms. Now when we say two sets are equal, two sets can be equal, two sets are equal. So two sets, suppose we have two sets A and B. When we say these two sets A and B are equal, A equal to B. If every element of A is in B and every element of B is in A, that's a condition. Every element of A is in B and every element of B is in A. Then we say A equal to B. Now mathematically, how do you show an element? Suppose there is an element, for example, suppose A is equal to set 1, 2, 3. Here 1 and 2 are 1, 2, 3 are the elements of A. So 1 is an element of A, we write like this. 2 is an element of A, we write like this. Similarly, 3 is an element of A. Is an element of this symbol that we use. This symbol that we use, element of. This is an element of. So two sets A and B are equal if the elements of A are in B and the elements of B are in A. Now let us take two sets A and B which are equal. You consider A is equal to the set of all x such that x is a root of the equation x square minus 5x plus 6 equal to 0. It's a quadratic equation. X square minus 5x plus 6 equal to 0. And you take another set B is equal to 2, 3. Now to check whether A equal to B or not. You know, B is very clear because elements are clearly written here, 2 and 3. Whereas A, the elements of A we have to find out because they are the roots of the equation x square minus 5x plus 6 equal to 0. Solving the equation x square minus 5x plus 6 equal to 0, you can see that x is equal to 2 is a root and x is equal to 3 is another root. So the roots of the equation is the same set B. So in this case is A equal to B. Both A and B are equal. The only thing is that they are written in two different forms. That's all. Now let us take another set. A is equal to 1, 2, 3 and B is equal to sum 3, 2, 1. Now, though the objects or elements written in a different order, that's the only difference between A and B. All the elements of B are in A and all the elements of A are in B. When we observe the same, we can see that all the elements of A are in B and all the elements of B are in A. But the order is different. Order is immaterial while we are writing a set. So here it is very clear that A is equal to B. So two sets A and B are equal sets. So when we say two sets are equal, two sets A and B are equal if every element of A is in B and at the same time every element of B is in A. In that case, we say the two sets are equal. Now, I told you already that there is a set is a collection which is well defined, the objects are well defined. So the question is whether there is any set which is not whether there is any collection which is not a set. That's the question. Can you find a collection A which is not a set? That means the elements are not clearly defined. Elements are not clearly defined means we are in a difficult position to say whether an object is in the set or not in the set. That's the meaning. So I will give you an example. You may be telling that A is a collection of beautiful flowers, is not a set. That may be sometimes wrong because once you define what is a beautiful flower, the objects are clearly defined. So we cannot use that example. But I take another example. Suppose A is a collection of all sets A, B, C, like that. All sets you take. That is, every element of this, every object in this collection is a set. Now the question, is this A a set? It's a collection. Is this set A? Is this collection A set or not? But you can see that this is not a set. Why? If this is a set, then this A should be an element of this A. This A should be an element because we have taken all the set of all collection of all sets we have taken. So this A should be in A. But this is not possible. So this is possible only if that object A is in A, and this is not possible. Not possible. Therefore, this is actually a paradox, we can say. A collection of sets cannot be a set. So this example you can cite while you are asked. Now, let us go to further. What is an empty set? Empty set. Is there any possibility for a set to be empty? Empty. It is also known as null set or void set. These terms normally used. Null set, empty set. A set is an empty set if it has no element at all. It is usually denoted by phi or empty brackets, empty braces. This way we write an empty set. Now an example let us take. Consider the set of all prime numbers less than 1. Set of all prime numbers. So S is equal to the set of all x such that x is a prime number less than 1 or less than 2. Now you can say there is no prime number less than because 2 is the least prime number. So this S is an empty set. S is an empty set, or we can write empty brackets. Now the set of all even integers in between 0 and 1. Set of all even integers in between 0 and 1. There is no even integer, there is no even integer, there is no integer in between 0 and 1. So that is an empty set. So there are plenty of examples you can cite for empty set. Now, some sets are finite. What is a finite set? When we say a set is finite, I am not going to the actual definition of finite. So you simply say that if it is has only a fixed number of elements. For example, as I have taken the set of all alphabets in the word mathematics, we know that set is M, A, T, H, E, then I, C, S. It is a finite set because 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements only in this set. So fixed number of elements. So a set is said to be finite if it has, a set is finite if it has only a fixed number of elements. Fixed number of elements. Fixed number of elements means maybe 100 elements, maybe 1000 elements, maybe 1 crore elements. So it is fixed, not varying. Such a set is called a finite set. Now there are plenty of examples. You can say the set of all factors. The set of all factors of the number 20. Now what are the factors of number 20? If you write the set in tabular form, 1 is a factor, 2 is a factor, then 4 is a factor, 5 is a factor, 10 is a factor, 20 is a factor. So these are the factors of 20. And it has fixed number of elements, say 2, 4, 6 elements only. Therefore, we say the set of all factors of 20 is a finite set. Now, some sets are infinite. Infinite set. When we say a set is infinite. A set is infinite if it is not finite. That's all. A set is infinite if it is not finite. If it is not finite. That means we cannot say that the number of elements in the set is some n, natural number, some number, 20, 30, like that we cannot say. For example, you take an example like this. Set of all rational numbers in between 0 and 1. 0 and 1. You know what is a rational number? A number which is of the form P by Q, where P and Q are integers. The set of integers is denoted by Z. P and Q are in Z. P and Q are integers and Q not equal to 0. These are the conditions for a number to be a rational number. In the set of all rational numbers we denote by the letter Q. The set of all natural numbers we denote by N. The set of real numbers is denoted by R. You remember these letters commonly used for naming the set of subsets of real numbers. The set of all integers Z, set of all rationals Q, set of all natural numbers N, the set of all real numbers R. Now let us go back the set of all rational numbers in between 0 and 1. Now what is the least rational number in between 0 and 1? Including, if you take including 0, you can take 0. So what is the next rational number? We cannot say. What is the last rational number? That we can say 1. But in between these 0 and 1, there are infinitely many rationals. For example, 0 plus 1, 1 by 2 is a rational number. 0 plus 1 by 2, 1 by 4 is a rational number. 1 by 2 plus 1 by 2, 3 by 2 is a rational number. So all these are rational numbers. All are in between 0 and 1. So there are infinitely many rationals in between 0 and 1. Therefore, the set of all rational numbers in between 0 and 1 is an infinite set. infinite set. This is not finite. It's an infinite. So there are finite set and infinite set. Many examples are there for finite and infinite sets. Set of all integers, let us consider, or set of all natural numbers, let us take. This is the set of all natural numbers is n, 1, 2, 3, etc. This set is not finite. It's not finite. It is an infinite set. Infinite set. The set of all integers 0, 1, 2, 3, etc. Similarly, minus 1, minus 2, etc. to the left side. This is the way we write set of integers. Negative integers and positive integers. So this set is an infinite set. Infinite set. Set of natural numbers is an infinite set. Set of integers is an infinite set. Set of all rationals is an infinite set. Set of all real numbers is an infinite set. Okay. So all these are infinite sets. And you will be learning in higher classes. There are two types of infinite. There is countable infinite and countable infinite. But I am not telling those concepts in this context. So there are two types of sets based on this concept, infinite set and finite set. Finite set means it has only fixed number of elements. A fixed number of elements. Countable. That's in the sense that there are 20 numbers, 20 elements, 30 elements, like that we say. Okay. Now let us go to another concept called subset. Subset of a set. Subset of a set. Suppose we have A is equal to set 1, 2, 3, 4. Now you take a set like 1, 3, 4. Clearly, all these that I am naming B, 1, 3, 4. You can see that all the elements of B are in A. All the elements of B are in A. So here we write B is a subset of A. Subset of A. Symbolically, we will write B subset of A. This symbol we use. There are two symbols that we use. B subset of A. This is subset equal to, this is subset, proper subset, we say, proper subset of A. A equal to set 1, 2, 3, 4, B is equal to 1, 3, 4. Now, set can be represented in many ways. Using diagrammatically, you can represent sets. These subsets, how do you represent diagrammatically? Let us see. And such a representation of sets in the form of figures is called the Venn diagram. Venn diagram. Now here we have A is equal to 1, 2, 3, 4, B is equal to 1, 3, 4. Then how do you write that? This is A. 1, 2, 3, 4. And B is 1, 3, 4. So this is our B. This is our B. 1, 3, 4. Or you can draw some, this way you can, first you draw B, 1, 3, 4, then 2 is outside A, B. So this is the way we write Venn diagram. Okay, we will discuss it in detail later, what is Venn diagram and all. So diagrammatically also we can write. The thing is that all the objects in B are in A. Then we say B is a subset of A. B is a subset of A. That is, if this is A and this is B, this is A, this is B, we say B is a subset of A. That is, every element of B is an element of A. That is, if you take any X, an element of B, this implies X is an element of A. This is the context. Set theoretically, if you want to prove a set is a subset of another set, you need to prove this one. You take any X in B and show that that X is in A. For example, set of integers is a subset of set of all rational numbers. How do you prove this? This can be proved very easily. We need not check all the elements in Z are in Q. It is not possible because there are infinitely many numbers in set, elements in set. So taking every integer and show that that is in Q is practically difficult. So we go for this idea. You take a typical element in Z and show that that is a rational number. I am taking an element x in Z. X is in Z means x is an integer. So it is something like x is equal to some integer that is in form m. M is an integer, maybe -3, 2, 5 like that. X is equal to m. Then that x you can write as m by 1. M by 1. M you can write as m by 1. Then m by 1 is of the form p by q, where m and 1 are integers, p and q are integers, q not equal to 0, q not equal to 0. Therefore, this is a rational number, m by 1. It is in q. It is in q. So, every integer you can write in the form p by q or m by 1, and that is therefore is in q. So, Z is a subset of q. This is how we prove the set of integers is a subset of rational numbers. Similarly, there is an inclusion in the case of set of subsets of rational numbers. That is, set of natural numbers is a subset of set of integers. Set of integers is a subset of set of all rational numbers. Set of all rational numbers is a subset of set of real numbers. This is the inclusion, general inclusion that we have in the field of numbers system, real number system. Now, see that q is a real number. Every rational number is a real number, and the real number in the sense that any real number that can be represented on a real line, all the numbers in R. Therefore, in Q, Z, and all the numbers R can be represented on a real line, That is why they are called real numbers. You might have studied these things in previous classes, marking the real numbers on a line by taking a suitable scale and marking +1, +2, +3 on the right side of 0 and -1, -2, -3 on the left side of 0 and so on. These integers, it's any rational number. If you have a 3 by 2 or 3.4, you can mark in between 3 and 4. Somewhere here it comes, so that is 3 and 3.4. So every real number, every rational number, you can mark on real line. Now there is another in between this. So this is R suppose, and this is Q suppose. Q is a subset of R. Now there are many real numbers that are not rationals. Such numbers are called irrational numbers. Irrational numbers. Sometimes denoted by Q complement. We'll write what is complement later. So Q complement, Q dash, or a set of all irrational numbers, some X, any letter you can use. So all the real numbers that are not rational. So what is an irrational number? An irrational number is a real number. Irrational number is a real number that is not a rational. That is not rational. This is how do we define a rational number. Now the set of all irrationals, the Q complement is also a subset of R. It's a subset of R. In fact, actually, R is the set of all real numbers. R is divided into the set of all rationals and set of all irrational numbers. Q is divided into set of all integers, and there are other types of rationals which are called fractions. And set of all integers again divided into negative integers, 0, and positive integers. This is the tree, real number tree, we can say in the field of mathematics. Okay. Now let us go back to some properties of sets. Properties. Some algebraic properties. as in the case of real numbers, as we add 2 and 3 and get 5, suppose we have two numbers a and b, can we add, can we subtract? Such kind of operations can we do in the set of sets. That is what we are seeking. Suppose we have two sets a and b. This is a and this is b, suppose. Now, the first operation, that is union of two sets. Union of two sets. This is the first operation that we do on sets. Union of two sets. What is the meaning of union? Let us see. The union of the two sets A and B, it is symbolically written as A union B by using cup A union B, which consists of all the elements in A or in B or in both, or set of all x such that either x is in A or x is in B or x is in both. That's the A union B. For example, A is equal to set 1, 2, 3, 4, 5, and B is equal to 3, 2, 6, 7. Then what is A union B? A union B is you pick up all the elements from A and B, right, in any order, no problem. 1, 2, 3, 4, 5 I have taken from A. Then 3, 2 already taken from, those are in B, already taken here. So 6, 7. When we write a set, we do not repeatedly write the same object. So A union B is 1, 2, 3, 4, 5, 6, 7. This is A union B. This is union of two sets. Union of two sets. So how do we mark using Venn diagram union of two sets? This is the union. You can see that there are elements like in A alone and B alone, and some common elements A and B. Just like here, A alone, 1 is in A, not in 1, 4, 5 is not in A. So A alone. 6, 7, B alone. But there are common elements 2 and 3. So without repeating that, we write the set 1, 2, 3, 4, 5, 6, 7. This is A union B. Now, another operation on sets is intersection. Intersection of two sets. Let A and B be two sets. Then A intersection B, we write symbolically like this. This is a set of all x such that x is in A and x is in B. X is in B. That is, the set of all common elements in A and B is denoted by A intersection B. By using picture, it is very clear. Suppose these are the two sets A and B, then this portion is A intersection B. A intersection B. For example, as we have taken earlier, 1, 2, 3, 4, 5 is A and B is 2, 3, 6, 7. Then A intersection B is equal to set 2, 3. These are the common elements in A and B. 2, 3. 2 and 3 are the common elements. So, using Venn diagram, how do we represent this? Let us see. 1 is outside in A alone. 4, 5 is also in A alone. Then 6, 7 are in B alone. And whereas 2 and 3 are common. 2, 3 you can write like this. 2, 3. So this is how do we write these sets using Venn diagram. So intersection. If intersection of any two sets, suppose, happens to be an empty set, then we say A and B are disjoint. Disjoint sets. Disjoint sets. A and B are disjoint sets. Disjoint sets. For example, let us take A is equal to the set of all x such that x is a positive real number, and B is equal to the set of all x that x is a negative real number. Then what about A intersection B? There is no number which are both A and B, positive and negative. Therefore, A intersection B is an empty set. Another example, P is equal to the set of all x such that x is a root of the equation x square minus 5x plus 6 is equal to 0, and Q is a set such that it is some 157. Then clearly P intersection Q is equal to empty set, because P is actually set 2, 3. When we write this P in tabular form, you get P equal to 2, 3, because 2 and 3 are the only roots of x square minus 5x plus 6 equal to 0. So P intersection Q is empty set. So you can cite many examples for empty intersection or disjoint sets. So we came across what is union, what is intersection. The next thing is operation is complement. Before that, let us take difference of two sets. Difference of two sets. Suppose A is equal to set 1, 2, 3, 4, 5, and B is equal to 3, 4, 7, 8. Then what is the difference? The difference is sometimes denoted by A minus B, or in some books it is written A backslash B, like this. So A minus B. It is the easiest way to write A minus B. So what is A minus B? A minus B consists of those elements in A which are not in B. Those elements which are in A but not in B. Here you examine 1, 2, 3, 4, 5 are the elements of A, 3, 4, 7, 8 are the elements of B. 4 and 5, 3 and 4 are in B. Actually, this 3 is here, 4 is here. So A minus B is only 1, 2, 5. Similarly, we can define what is B minus A. Those elements in B but not in A. 3 and 4 are in B, so not in A, 7 and 8. So 7 and 8. Actually, A minus B is a subset of A. B minus A is a subset of B. That's the thing you understand. A minus B is, how do we define A minus? A minus B is equal to the set of all x such that x is in A and at the same time x is not in B. This is A minus B. Okay, another wonderful thing that you can verify is that this union, intersection and difference. You can connect all these things. Union, intersection and difference. This is A. This is A. This is B, suppose. Then we know this is A minus B. This is A minus B. This is B minus A. B minus A. This is A intersection B. Their union is A union B. So we can write from the figure, it is very clear that A union B is A minus B union A intersection B union B minus A. B minus A. This you can verify with some examples. A is equal to 1, 2, 3, 4. B is equal to, as previously we have taken. If you take A and B, you can verify also with some examples. A union B is equal to A minus B union A intersection B union B minus A. Now, there are some sets that you can see in this set of real numbers, subsets R. That is intervals. Intervals are actually certain subsets of R. For example, The open interval 1, 3. Open interval 1, 3. What is open interval 1, 3 means? All the real numbers x such that 1 less than x less than 3. All the real numbers greater than 1 at the same time less than 3. Such a set we call open interval, or generally we write open interval AB equal to the set of all x in R such that A less than x less than B. Diagrammatically we can write like this. This is suppose A and this is B. This is the open interval. Here A and B are not included. All the real numbers in A and B are in the set A and B. Another set is closed open interval. It is set of all x in R such that A less than or equal to x less than B. That is, A is also an element, but B is not an element, and all the real numbers in A and B are also elements of A. Similarly, left open, right closed is set of all x in R such that A less than x less than or equal to B. And the AB like this is a closed interval AB. Here all the real numbers such that A less than or equal to x less than or equal to B. These are some subsets which are very important in the real number system, subsets of R. And the whole R is also an interval. It is written as minus infinity plus infinity. Over R you can say the set of all x in R such that minus infinity less than x less than infinity. This way we can write R. So these are some subsets of R. Subsets of R. Some particular subsets of R called intervals. Intervals in R. Now, what is a power set? Power set. Suppose we have A is equal to 1, 2, 3. Then power set means power set of A. It is denoted by PA. We can write PA. It is a set actually. It is a set consisting of subsets of A. The set of all subsets of A is called power set of A. PA is set of all subsets of A. All subsets. For example, here A is equal to 1, 2, 3. What are the subsets of A? Now, when we write all the subsets, empty set is a subset of any set A. Phi is a subset of A. Empty set is a subset of A. Because if you take an x in phi, then if you take any x in phi, then it is clear that x is in A because there is no x in phi. Phi means it is an empty set, there is no element, there is no x. So if you assume that there is an x, if at all there was an x, that x would be in A. That sense we can say phi is a subset of A. Empty set is always a subset of any set. So phi is a subset. Then subsets having single element 1, 2, 3. Then subsets having two elements 1, 2, 2, 3, 3, 1. Then the last, all the elements 1, 2, 3. I mean the A. Then this set is called power set of A. So when you are asked to write the power set of some sets given, you write all the subsets in the set as a set, then that is power set. So power set is a set of all subsets of A. Now another question here comes is that if A has some n elements, how many elements will be there in the power set? P of A. Power set of A. You can see that there are 2 raised to n elements. Here you can see 1, 2, 3. There are 3 elements. The number of subsets is 1, 2, 3, 4, 5, 6, 7, 8. That is 2 raised to 3. If A has number of elements in A and A is equal to 5, then the power set of A, cardinality, I mean the number of elements of PA is 2 raised to 5, 32. How do we get this? You can easily check. Because if there are n elements in a set, then this n elements can be selected such a way that no object, one object, two objects, three objects, four objects, like n objects. This way, if you choose from these n, total n objects, how many ways you can choose? That's the question. How many ways you can choose objects from n, considering that selection, no element, one element, two element, three element, like that. No element, it is only one set, that is empty set. And out of n, suppose there are n objects, how many ways you can select one object? You can take the first object, second object, like that. So we can take n ways you can take, n ways you can take. Then you take the two objects, that you can take two objects out of three. Suppose there are three objects, A, B, C. How many ways you can choose? A, B, A, C, B, C. Three ways you can choose. That is actually written as 3C2. It is a permutation that we will be discussing later. Permutations and combinations coming under that. So here NC0, NC1, NC2, like that, NCn. If you add all these things, you will get 2 raised to n. This we will prove later, not now. Anyhow, you just remember here, if I say set having n objects, the number of elements in the power set is 2 raised to n. So if A has 5 objects, 5 elements, or the cardinality of A, the number of elements of A is 5, then the power set has 2 raised to 5 objects. Let us take an example. Write the power set of the set of all x such that x is a root of the equation. X cube minus 1 is equal to 0. X is a set root of the equation x cube minus 1 is equal to 0. Or let us take, because x cube minus 1 is a third degree equation, solving may be difficult sometimes. We know these roots are actually 1 omega square are there actually, but you have not familiar with these complex numbers and all. While you learn complex numbers, you will be coming across all the roots, but the real roots, let us take an example, x square minus 1, let us take, that's better. So the roots are plus 1 and minus 1 are the roots. So this set is plus 1 minus 1. Now you can write the power set of this set. Power set consists of empty set, then 1, then minus 1, then 1 minus 1. This is the power set of this set of all. Suppose this set is root R, then P of R is 5, 1, minus 1, 1, minus 1. Another example, write down the power set of this set of factors of 12. Now what are the factors of 12? Find factor f is equal to 1 is a factor, 2 is a factor, 3 is a factor, 4 is a factor, then 6 is a factor, 12 is a factor. So these are the factors 1, 2, 3, 4, 6. How many? 1, 2, 3, 4, 5, 6 elements are there. Then the power set Pf has 2 raised to 6 elements. 2 raised to 6 elements. That is 64 elements. 64 elements are there. Now what is the power set P of f? The number of elements in f is a set is very large. It is very difficult to write the power set, but we can write for this f. First one is empty, then set 1, set 2, set 3, etc. set 12, 1 subsets having 1 element, then subsets having 2 element, 1, 2, then 1, 3, 1, 4, 1, 6, 1, 12, 2, 3, like that. Last 6, 12. Then 1, 2, 3, like that. You write. having 3 elements, having 4 elements, having 5 elements, having 6 elements. All these sets you can write, then you will get a power set. Now, what is universal set? Universal set. Universal set is a set of all sets under consideration. Suppose in a special context we have 3 sets A, B, C. A is equal to some 1, 2, B is equal to 2, 3, 5, 7, C is equal to 1, 3, 5, like that suppose we have. So these are the sets at present we have in our hand. So what is the universal set? Universal set is a set you take which is larger than all these A, B, C. That is, you consider a set U such that all the sets under consideration A, B, C are subsets of U. Or the least universal set that we can make from this A, B, C is set 1, 2, 3, 5, 7. 1, 2, 3, 5, 7. This is a universal set for A, B, C. Or even if you add 6, no problem. This is a universal set. Universal set, Venn diagram, using Venn diagram, it is denoted by a rectangle. This is universal set. Then there is an A here, which consists of only 1, 2. Then B is there, consists of 2, 3, 5, 7. 2, 3, 5, 5, 7 is there. Then 1, 3, 5. 1, 3, 5. 1, 3, 5 is C, no? It is that way you can write it. This is 1, 3, 5. This way you can write 1, 3, 5. So this is the Venn diagram that we can write for this ABC. This is the universal set. There is a 6 outside all these subsets given because 6 is not anywhere in ABC. So you mark 6 outside these sets ABC. This is A, this is B, this is C, this is C, like that. Now, what is complement of a set? That also, complement of a set. The complement of a set is always with reference to the universal set. So if A is any set and U is the universal set, then complement of the set, we can write A complement, AC, like that. It is U minus A. This is U minus. Suppose this is U and this is our A, then A complement is this one. This is A complement. This shaded part is A complement. A complement. A complement. This is A complement. So how do we define A complement? A complement is equal to the set of all X such that X is in U but not in A. X is not in A. X is not in A. But X is in U. X is in U. Those X in U for which X is not in A. This is when this U changes, A complement changes. For example, I told you the set of all rationals is a subset of the set of all real numbers. So what is Q complement? Here R is the universal set. Q complement is those real numbers, those elements in R which are not in Q. Or X in R, but at the same time X not in Q. Not a rational. That is Q complement. Or Q complement is R minus Q. R minus Q. R is the universal set in this case. So complement. Another thing that you have to understand that if there is A is any set and A complement is its complement, then their union will be equal to the universal set. A union A complement will be It is very clear from the figure. This is A, this part is A complement. Their union is U, universal set. A union A complement is U. And at the same time, A intersection A complement is equal to A intersection A complement. That is equal to empty set. There is no common elements in A complement and in A. A intersection A complement is empty. That's A and its complement are disjoint. A set A and its complement are disjoint. Now, one more thing that we will discuss here. After that, we'll be winding up in this session. Here we have talked about what is a set. How do we write a set? What are the different forms for writing set? What is the notation for writing a set? Then what is an empty set? What is an equal set? What is subset? Power set, all the things that we came across. Now, regarding these concepts, suppose there is some important result called concerning this complement, intersection, union, etc. The first result is that if A and B are any two sets, suppose, then A union B complement is equal to A complement intersection B complement. This is one result. A intersection B complement is equal to A complement union B complement. These results or laws we call De Morgan's law. De Morgan's law. A union B complement. It is very well explained by using a figure. It's very easy. This is A and this is B, suppose. Then this is A union B. A union B. This is A union B. Its complement is the not shaded part. This part. Or I can shade with the blue color like this. This part is A union B complement. And that is nothing but A complement intersection B complement. This is A. So this is A, this is B, this is A complement, this is A complement. B complement. A complement means you have to consider this part also, okay, white part, or this white part. Then what is B complement? B complement is I am shading with the green part. What? Their intersection is, common area is, I shade with the yellow part, this part. This is their intersection. Green and white is the same as the blue shaded here. So A union B complement is A complement intersection B complement. How do we show this? We can show it. A union B complement, we want to prove it is A complement intersection B complement. You know, two sets P and Q are equal. If you want to prove, you take any X in P and show that X is in Q, so that P is a subset of Q, and you take any X in Q, show that X is in P, that is Q is a subset of P. That means two sets P and Q are equal if these conditions are satisfied. P subset of Q and Q subset of P. If these two conditions are satisfied, or this way conditions are satisfied, we say P is equal to Q. Here we want to prove A union B complement is equal to A complement intersection B complement. So you take any X in A union B complement, which implies X is not in A union B. X is not in A union B. This implies X is not in A and not in B. X is not in A and X not in B, which implies X is not in A means, which implies X is in A complement and X in B complement. Not in A means A complement. It implies X is in A complement intersection B complement. Therefore, this shows that A union B complement is a subset of A complement intersection B complement. Clear? Now we have to prove the other side. You take X in A complement intersection B complement, show that X is in A union B complement. Okay. Now let us take X in A complement intersection B complement. This implies X is in A complement and X is in B complement. This implies X is not in A and X is not in B, which implies X is neither in A nor in B. So X is not in A union B, which implies X is in A union B complement. And therefore, A complement intersection B complement is a subset of A union B complement. Previously, we proved A union B complement is a subset of A complement intersection B complement. And therefore, from these 2 and 1, you can see that A union B complement is equal to A complement intersection B complement. This is De Morgan's law. Similarly, we can prove A intersection B complement is equal to A complement union B complement, the same way. I am not proving it, you just try for this A intersection. This law is called De Morgan's law. And another law concerning this complement is A complement complement. I forgot to tell you that A complement is sometimes in some textbook it is denoted A dash. That we have the A dash. This is another notation for writing complement. I use AC, A complement. A complement complement is A. So here also you have to prove the same thing. You take any X in A complement complement, which shows that X is not in A complement, which shows that X is in A. Therefore, A complement complement is a subset of A. And the reverse also you can prove. X is in A, then X is in A complement complement you can prove. Thus, you are getting this relation. A complement complement is equal to A. Venn diagram, if you use, this is A, this is A complement. A complement, this is A. Again, A complement complement, there is complement of the shaded part. This is not shaded part, there is A. There is A. So, A complement complement is A. So, these are some of the results concerned with complement, De Morgan's law. With this, I wind up this session, set theory preliminaries. We will be discussing the later sessions of set theory in the next session. Thank you very much.